All right, let's talk about something that can literally make or break a scalable app, but it's so often just an afterthought. API pagination. And we're going to figure out, are you really doing it right?
So let me just start with a question for you. What if that simple page number you always see, the one that seems so harmless, is actually a performance time bomb just ticking away, waiting to wreck your app? And look, that's a serious question. And by the end of this, I promise you'll have the answer.
So first things first, we have to talk about the sheer chaos of data. We've all felt that temptation to just fetch everything in one giant request. But let's be real. When that dataset balloons from a few thousand to millions of rows, that's not just a bad idea, it's a guaranteed recipe for a total system meltdown.
And that meltdown, it's not some abstract concept. We're talking about real users staring at endless loading spinners, servers just giving up and throwing 504 gateway timeout errors. And you get to watch your cloud bill just skyrocket from all that runaway memory and CPU. It's an awful experience for your users and a complete stability nightmare for your whole system.
So what's the fix? Well, it's pagination, of course. It's a simple idea, right? We just break that massive, chaotic data set into smaller, much more manageable pages. But, and this is a big but, while the concept is easy, the implementation, that's where things get really, really tricky. This isn't just a UI feature. It's a fundamental architectural decision that dictates your app's performance and its ability to scale.
So when you need to paginate, what's the first tool almost everyone reaches for? Yeah, it's position-based pagination. It feels so intuitive, it's everywhere you look, and as we're about to find out, it has a hidden, very dark side. Come on, we've all seen this a million times. It's the classic API call you find everywhere. Question mark, page equals 3 and size equals 20. Hey, give me the third page with 20 items on it. It's simple. It's easy for us humans to read and understand. And you know what? It gets the job done at first.
But what's really happening in your database when you make that call? That simple little page equals 3 is just a convenient abstraction. Under the hood, it's being translated into an SQL query using limit and offset. So to get page 3, we're really telling the database, hey, skip the first 40 records, then give me the next 20. Seems logical enough, right? Well, not quite.
And that right there, that brings us to the trap. The deceptive, beautiful simplicity of offset is exactly what makes it so incredibly dangerous. It works perfectly, right up until the moment it catastrophically fails. And here's why it's so sneaky. If you ask for an early page, like page 2, it's lightning fast. An offset of 10, that's nothing for any modern database. It feels efficient. It feels like you made the right choice. It fools you.
But just watch what happens when a user wants to dig deep into those results. To get to page 10,001, we suddenly have to offset 100,000 records. This isn't a quick lookup anymore. At this point, your database just hits a wall, and you've got a disaster on your hands. And here's the absolute killer detail. A database can't just magically jump to row 100,001. That offset command forces it to actually fetch all 100,000 of the preceding rows from the disk, load them all into memory, sort them, and only then can it throw them all away to give you the 10 rows you actually wanted in the first place. The query's cost just explodes as the offset grows. It's a performance nightmare. Oh, and it gets so much worse. Performance isn't even the only problem. Imagine this. Your user is looking at page 1, and the last item they see has an ID of 100. Cool, but before they click to page 2, a brand new item gets added to the very top of the list. Suddenly, the entire dataset has shifted down by 1. So when they request page 2, what's the first item they see? ID 100. Again. It's a duplicate from the page they just left. Now your user is confused and your data feels broken.
Okay, so if offset is our flawed hero, who's going to save the day? It's time to meet the real hero of this story, a much more powerful and scalable approach known as Keyset or cursor pagination.
This approach, which you'll hear called Keyset or seek pagination, completely flips the logic on its head. We stop telling the database how many rows to skip. Instead, we start telling it where to begin looking. We use a stable, unique value, like the ID from the last record we saw, as a reference point to fetch the next set of results.
And this slide just says it all, doesn't it? It's a total paradigm shift. On the left, you've got that slow, painful scan and discard method of offset, but on the right, the value-based approach uses a where clause. By saying where ID greater than 123, we're telling the database to use its index to seek directly to that spot and just start reading.
It doesn't care if it's 100 rows in or 100 million rows in. The performance is consistently, beautifully fast.
Now, you might hear the terms Keyset and cursor thrown around like they're the same thing, but there's a subtle and really important difference. Keyset is the mechanism, the idea of using a value like an ID as a reference point. Cursor pagination is the more advanced implementation, where that value is wrapped up in an encoded, opaque string, a cursor. This adds a great layer of security and flexibility because it hides your internal database details from the client.
But there's one absolutely critical rule to make this whole thing foolproof. You need a tiebreaker. Okay, imagine you're sorting by a created@at timestamp. What happens if two items get created at the exact same millisecond? The order becomes ambiguous, and you're right back to having chaos with missed or duplicate items. The solution? You have to add a second unique column to the sort, like the item's ID. This creates a perfectly stable, deterministic order and guarantees that no items are ever skipped or duplicated. Ever.
Okay, enough theory. We've covered how it all works. Now let's get practical and translate all this into a simple framework so you can start doing pagination the right way in your own projects.
And really, the key takeaway here is that context is everything. There's no single best method for all situations. Got a small dataset that never changes? You know what? Offset is totally fine. But the second you're dealing with a large dynamic dataset, think of a social media feed with infinite scroll, Keyset or cursor becomes absolutely non-negotiable for performance. This framework helps you pick the right tool for the job. And this isn't just some academic exercise. The biggest names in tech live and breathe these robust methods. Stripe's API is just a masterclass in how to implement cursors. Twitter, or X, completely relies on an opaque pagination token to handle its insane real-time fire hose of data. And then you have companies like Merge.dev who've built their entire platform around solving the headache of dealing with everybody's different pagination styles. So if you're going to take just one thing away from all of this, let it be these three pillars. First, selectivity. Always use a where clause to seek, never an offset to scan. Second, stability. Make sure your data has a rock-solid, consistent order by always using a unique tiebreaker. And finally, efficiency. Think beyond just pagination and watch out for related problems like the N+1 query pitfall. If you can nail these three, your system will be built to scale. Which, of course, brings us right back to where we started. Now that you know about the offset performance trap and you've seen the power of Keyset pagination, I've got one last question for you. Will you ever look at a simple .page equals to request this same way again?